Okay, let's start. So today we'll focus most of the time on cumulants, and we'll talk first about symmetric distributions and what we'll call soon even elements, which we'll mostly use to repeat the definitions you've seen in the lecture so that they sink in. Then we'll talk about the additive convolution and define what a free Poisson element is. And if time allows, we'll end with some incredible facts about the free Poisson. So we'll start with, we reached so far that we can talk again about distributions and not only about combinatorics. And we think about probability distributions on the reals such that they are symmetric for plus and minus. So I think about probability distribution mu, where mu of t equals minus t. Okay, we've seen a few examples of these already, the semicircle and others. What would be the algebraic description for such an analytic distribution?
The algebra?
Yes, if you think about the moments.
So the other moments must be zero.
Exactly. So we say that an element, if I have a non-commutative probability space as usual, phi, we say probability space, say that an element x in the algebra is even if following holds. So for every natural k, the moment x 2k plus 1 is 0. Okay. All odd moments vanish, and we'll denote that by the rest of the tutorial. We'll call that m plus 1 of x. And when x is clear from context, I'll eliminate it on the. Okay, so this is the algebraic description for what happens if I have the symmetric condition. And we call these even elements. Okay, and the first thing we'll need to note, so let's call it exercise 1 or claim 1, that if x is even, then all odd cumulants also vanish. Okay, so we do this especially to recall the definition of cumulants. So I want to say that the kappa k plus 1 of x for every k will also be 0. So if k is even, odd cumulants vanish. And how do we prove that? Well, it's going to be simple, just writing down the definition. So the 2k plus 1 cumulant of x is the sum over all non-crossing partitions of k plus 1 of m pi. Now recall that this is defined by the numbers here. Okay, and I'm here times the Mobius function of pi and one element of 1. Sorry. And now I don't care about the Mobius functions. For this, if I want to have a partition of an odd number of elements, at least one of the parts will be odd as well. Okay, so m pi, or m pi equals the product of all the parts in pi of m size of the part And if this is a partition of an odd number of elements, at least one of these will be odd. One of the parts will be odd, and the moment will vanish. Okay, so for this reason, this is a sum of zeros times the modulus function, and this is okay. So this is just a warm up.
So kappa 2k plus 1 is just, we denoted it in the class before by kappa of xxxxx.
Okay, so we won't need it much in this tutorial, but kappa n of x, I sometimes use the parentheses, sometimes not, would be the kappa n function of only x. And we call that, I mean, the cumulants are functions, just as phi is a function or functional of, like I have a parameter n here. But when I say when I say the moment of an element, I don't say, well, the moment function applied on x to the, I'm just saying this is the moment of x, so this is the cumulant of x. This is slang, but it's commonly used. So as all the odd moments vanish, all the odd cumulants vanish as well. So I can say, okay, this element is determined by its even cumulants, and we denote by alpha k the alpha k of x, the 2k cumulant of x. I only care about the even ones, and I call this the determining sequence. Determining sequence of an even element x. Okay, and know that as always, if we have a sequence of numbers indexed by k, we can also denote alpha pi as the product, as usual, the product of all the parts in pi of alpha of this side. Okay, for a partition. This is the usual notation. Okay, so the second claim we want to prove, and here we'll need some more machinery from class, is the following: that if x is even, determining sequence alpha k, then I want to ask questions about the element x squared. What I want to say is that, write down the kth cumulant of x squared. Let's have it with a different color here. Okay, now ask about the cumulants of x squared, which is, okay, the claim is that it equals sum over non-crossing partitions of size k of alpha pi. Make sure I'm stating this correctly. Okay, so the cumulants of the squared element are, it looks like sort of like the moment cumulant formula, but it's not quite, because these are cumulants and these are cumulants too. I can get it from the cumulants of the original one.
So is it k or 2k?
K. And it sort of makes sense because this is the square.
So it's not, it can't be even, right? Because it's only positive.
Yes, you get, like, if you think about an even this symmetric distribution. So if the original one was, let's say, the semicircle, this is not a good drawing of the semicircle. So the square, you would expect it to look higher over here, and you expect the square to look somewhat like this. Maybe it should be, yes. The proportions here are wrong, but it's only on the positive side, and you only look like, you know how the moments look. This is pretty easy. We'll talk about it soon, but the cumulants have this formula, and for proving it, we'll first write down the definition. So what is kappa k of x squared? I'll do the purple one for the last time. Squared, this just equals a cumulant of, I don't remember if I need the square brackets or the regular ones. I just the regular ones. And this also equals kappa k of xx x, and this is what x squared means. And now this maybe already hints you what we're aiming to do here. We'll recall a claim we've seen in the lecture today, which I'll write down in try to write down in its full generality. So let me be careful here. So if I have A1 equals 1 up to M1, A2, which equals M1 plus 1 up to 2, up to A, or what was the last index? Oh no, it was M was this one. This were I's, right? I'll keep the same notation. I1, I1, and I2. This is I m minus 1 plus 1 up to I m, which equals n. I have these sets, and I want to understand what is the tau cumulant of A1 up to AM. Okay, tau is now a non-crossing partition of M elements. M is less than N. And then this equals the sum of the pi cumulants of the original elements A1 up to AN, where, okay, I'm sorry. These are, this is not correct as I wrote it. These are the parts, and what I really want is that, not this one, but rather A1, A2 up to AI1. Okay, these are not the, these are just the partitions. And the element I'm looking at is this element here, so on for the others. And the question is, which pi's should I iterate over? And so here, tau is of the type non-crossing M, and here I'm looking at pi's which are non-crossing N, fulfilling the condition that pi, or I'll make sure I'm doing this correctly, but the zero element lifted according to this lift equals the identity. Equals, I'm sorry, lifted tau. I'll use it for the identity, but the lifted tau. Okay, let me make sure in the notes that I'm doing it properly, but Yes. Okay, so this is a general theorem we've seen. And now in order to apply it to our case, we need to understand what are the AIs. And from this together, what is lifted 0 and what is tau that we're looking at. So translating it here, we need, what tau we care about? We care about the identity element of K, not identity, the one of K, right? Because I only care about the number here, and number means the largest element in the lattice. And the AIs are all the X's here. So the 0K lifted just means the following partition. Right? Because I have 2K elements, and each one of those represents the pair of X's over here. Okay, so this is the 0 element lifted. And now what do I get by the theorem? So now I apply the theorem here. And I get that this equals the sum over non-crossing partitions of size. What size do I care about here? 2K, right? Such that these pi's are, if they are, let's have a name for this one, will be denoted by sigma. Then sigma or pi equals the one element lifted, but this is just 1, 2. Right, the one element lifted is always the one element. And I have here the case cumulant, the pi cumulant of, okay, so here I have all x's, so I'll just call it the pi cumulant of x. Okay, so this starts to look like what we aim for. The cumulants have something to do with the sequence, but I need to determining sequence, but I need to translate this pi over non-crossing k to this pi over non-crossing 2k with the additional condition. Okay, so it's kind of weird. So let's find the set G. And what is this set going to be? All pi's in non-crossing 2k, such that two conditions need to hold. One, this one, pi and sigma generate the one element of 2k, and also that k pi doesn't vanish. And I want to claim that this set is pretty easy to describe. It's going to be all the elements pi. I would like to take this and take it a little bit down. I'm not able to, so I'll just squeeze in a different color here. So my elements pi that will fulfill this will be the ones greater in the lattice than the following one. This partition. This is a pairing, but this wasn't a requirement. Okay, or in other words, I want to have two conditions. First, I need the first one to be connected to the last one. And then I need every even one to be connected to the next. And all the rest is free. You can attach whatever is already attached. That's for free. Let's try to figure out why is this. So or we'll just stare at drawings now. We're not going to prove this in words.
Possible to prove it. I can see like why it's true. Like,
so it is possible. It's done in the book, but let's try to think about it and be convinced that it is correct. So let's imagine the first one is not connected to the last one. Let's say we have pi in G, such that let's say one is connected to somewhere here, and this is not the last. There's still more elements here. Now we first need to see that this index has to be even. Because if it is not, somehow another part of the partition is either here or both will be odd, and if something is odd, then the cumulant is going to vanish. Okay, because I'm going to have a partition of some odd number within. Oh, let's just look at this side. Okay, so if this is the last one, here it's more complicated because this is not a pairing. But if you just look at this part, if you have odd number of elements here, cumulant vanishes. So this means that not only you're not connected to the last one, you're not connected to 2k minus 1 either. So one is not, so the last two at least are not connected. And you're connected to some element, let's call it, I don't know, 2m over here. And from here on out, there's something else happening, but you know that these will not be connected to each other because they're not connected in sigma either, so this condition won't. So one needs to be connected to k. And once you move on, you do this like pick an index, and you sort of do the same thing.
look at the most left one. So we get the next one because it isn't, it has to jump over it.
Exactly, and this will hold true for any index that you choose here. It will be heavy. Okay. So these are exactly the elements. I hope you're convinced. And now what I said the set G is just the elements pi that satisfy this condition, that they're greater than this partition. And what I want to say is that while you see that this pi, that this basic partition is a pairing, and you can also see that pi's satisfying this condition are in bijection to non-crossing of k.
Wait, actually, this didn't prove that k pi isn't zero. It might still be zero.
Right, it might, okay. It
G contains the set. Like what you described contains the set of all of these.
point.
But you can sum over G instead
Good
of
point.
yeah.
Good point. First of all, this will be enough for me.
Yeah.
The fact that it contains it, I think it's going to be, I mean, some of them might vanish.
Yeah.
That's correct. Even though I'm pretty sure that unless something is really redundant here, all the alpha k's would be positive. But I'm not 100% sure, so I won't. But this is going to be enough. And this set, if you look at it closely, it's in bijection with a non-crossing of k. We already know that things in non-crossing partitions behave nice cyclically, so you can move the 2k to the first place. Then the structure of the pi satisfying it is just you merge every pair to one element, and then you just have a partition over them, a non-crossing partition over them. Non-crossing won't change anything here. And from here on, it's basically like making sure that not only this is in bijection, but also the kappas behave nicely. So now I need to understand what is kappa of pi in terms of, well, maybe I need to name it differently so that I can speak about it in comparison to this one. Let's change this one. And you notice that every part in this pi, by definition, will contain an even number of elements where you partition pairs. And each one of those, the number of them would be exactly twice the number of elements in the 2K partition. So actually this, something stronger than this actually holds than this bijection is that the value of this K pi be exactly alpha of tau of the relevant part of the relevant partition in non-crossing K. So I'm not writing this down explicitly, but I hope this is clear from the drawing here. Okay. So this was here especially to play with the definitions and the theorem we've seen in the lecture. But now we're going to see an application of it and ask if I have, this is true for a general even element X. Now I ask what is the distribution of, what are the cumulants of S squared, where S is a semicircular element. And okay, so what I want to know is the kappa K of S squared. Now let's recall what we know about semicircular elements. So have the moments K, and we have the cumulants kappa K. We have the semicircular element, and we have the semicircular element squared. The moments here, we already know that they are sigma to the K of some sigma times the Catalan number of K half. This is true for the even ones, or just 0 for the odd ones. And for S squared, trivially, it's going to be just sigma to the K, the K's Catalan number. This is almost by definition. No. Because what is the kth moment of S squared? It's the 2K moment of S. This is just by definition. Confusing, like all the odd ones like don't exist here. Because this is already squared. And the cumulants of the semicircular element, we've seen that they equal sigma squared times delta of K and 2 and K. Right, the second one is sigma squared, and all the other ones are log. And we ask about what's this one over here. And I don't have an intuitive answer for that. I'll just calculate it by the formula that we've just seen. So this equals.
Oh, no. S squared isn't a semicircle, or S is a semicircle?
S is a semicircle, and S squared is the square of a semicircle. We're trying to figure out, I mean, we know how it looks like. If this is the semicircle up to near the scaling here, we expect this one to be the square of the semicircle. By this formula, this equals the sum over tau non-crossing K of the kappa. Okay, we can think about these ones as so if I want to translate it to the alpha language, so alpha K equals sigma squared times what? Delta 1. Right? Because I ignore the odd ones, and the alphas enumerates the even cumulants of the even element.
Over two then?
No, the cumulants are they look like this. So the alphas look like this. This is just notation.
You could do 2k over 2, but it's the same as 1k. It's 1 only when k is 1.
And here I want to use, I'll write alpha tau, but let's think about these alpha taus. Which ones out of them actually survive? Because alpha tau is just, write it down explicitly, so tau non-crossing in k. Then I have the product of the parts of tau, alpha to the size of the part. But if the part is not of size 1, it will vanish. So I need all the parts to be of size 1. So I only care about the 0 element. So this would equal, so what would be the 0 element? I have sigma squared exactly k times. So this is sigma to the 2k. So now weirdly, the cumulants of the semicircular elements squared are sigma to the 2k. And I don't have anything smart to say about it, but it's in a different color here, and let's keep this thing in mind. Like what do we, like this, because this is going to appear in the next thing we're going to do. Okay, so encoding, having a semicircular element, we have a very simple description for using cumulants. If I square it, things start looking funny, and we'll try to understand what this is. So now I want to talk about something else, which is a Poisson element. So first, let's describe, just for to get some context, we know that a binomial random variable looks like we have capital N choose k, e to the k, 1 minus p, the n minus k. Right, p is some distribution, some probability between 0 and 1. And we think about, and this is in a binomial random variable. We think of k as like the number of occurrences of the thing we're counting. And it is known that, well, if you think about this p as, let's say, pn, might change with the number of events. And if we think about times pn converging some number lambda as n goes to infinity, we know that this distribution converges to the Poisson random variable. I'm not going, this is just like maybe intuition if you remember probability theory of what we're going to do. So this converges to something that's called the Poisson random variable, for which the formula is, so that I'm not getting this wrong, e to the minus lambda to the k over k factorial. And there's another, so this is called Poisson. And there's another way to describe this Poisson element, which is by what's called the law of rare events. And the law of rare events looks like this. So I'm not expressing, I will use n, but I'm not going to use p. I'm going to use lambda directly. So it's going to be 1 minus lambda over n. Delta 0 means just don't count this, or this event is not, the event is not happening, plus lambda over n delta 1. And we take this whole thing to the convolution power n. Meaning that if this is one, this is similar to what we did for the central limit theorem. We have one element. This is kind of a normalization. We have one element and we add up. This is a sign for the convolution, means we add up independent random variables with this distribution. So if I have x, a different color. If I have element, let's say AI, that's distributed by this distribution, and I look at the sum of the AIs, I goes from 1 to n, and n goes to infinity. I'm having a limit here as well. The limit of n goes to of this distribution. And apparently this produces the same Poisson distribution. Okay, I'm just giving it as a fact here. What I want to do here, even if you don't remember any of this, you do remember that the Poisson distribution exists. There's a very funny Wikipedia article for it. And what I want to do is the analog case for free Poisson element, which means that instead of the AIs being independent, I want to make them free. So what do I mean here? Instead of putting the convolution sign here, the classical convolution, I'm going to put the free additive convolution that we'll describe today. And what I mean by that, I'm asking what is the distribution? And this is a similar question to the one we asked about the central limit theorem. I take AIs, I sum them with some normalization. I take the limit, the number of elements to infinity, and I ask what is the distribution of this element, which I'll call P for Poisson. And I'm asking what's the distribution of this P. And for being a little more general, because I can, there's another parameter here that's called the step. So I can write some alpha here, which may be 1, but may also not be. Okay.
So what do you mean by such an element in the abstract case of commutative algebra and so on?
Okay, so when I have this, I'll write down the moments in a second, in a moment, but what I mean here, an element in a non-commutative probability space, a self-adjoint one, with this, so I have an element, let's call it xn, with, for a fixed n, I have an element with this as its analytic distribution. In a minute, I'll get the moments out of it. And then I'll say, okay, the element is the element with these as its moments.
I don't understand what's delta 0 and delta alpha.
Oh, okay. The delta function is like if you want to have an element with a probability half of being, let's say, 5 and probability half of being -3, then you can write
5 plus half delta minus 3.
Exactly. So you can write this probability distribution as half delta 5 plus half delta minus. So this is notation for discrete probability distributions. Yeah, I forget what notations are common and what aren't. This is very standard in physics like that. Okay, so now the 0. So this means in the context of a binomial random variable, this means the event didn't occur. And here it says if it was 1, it was just it occurred. If it's alpha, it's like the amount that the occurrence gives you. Okay, so I have this xn, and we want to ask what is the kth moment of xn. Okay, which is, I mean, if it was I started with the distribution, but if it was a non-commutative probability space, I would ask what is phi of xn to the k, right? But I don't really need this here. So how do I calculate? Now this is standard probability. Nothing.
Xn is the element whose distribution is AI.
Yes, for fixed n. Okay, so
Its distribution is the convolution.
no, not yet. Just one element. Oh, not yet. No, just xn and or an. Let's call it an. Yeah. Oh, this one. Excel. Never mind. These are elements with this distribution in the analytic sense. I'm mixing it up here. So, but the calculation has nothing to do with the free probability or with non-commutative probability space. It's just with this distribution in mind, calculating its moments. So I have with this probability, I have 0, so it contributes nothing to the moment. And with this probability, I get what? For the kth moment, alpha to the k. First moment is alpha, the second moment is alpha squared, and so on. And now I'm asking about the kth cumulant, per cumulant of the same element. And now I'm just going to use the formula. So this is the sum over non-crossing partitions of k elements of the, let's write.
Should it be lambda over n to the k times alpha to the k?
No. This is like with probability. With this probability, you get 0, and with this probability, you will get alpha to the
But
k.
then you take the power of this element.
So don't mix the value. The thing that you take into power is the x-axis here, but the probability stays the same, right? Yeah, it's confusing, but this is the right thing. Let's write m pi of this element times the Mobius function, Mobius of something, pi m 1k. So I'm going to split it with the first one. So I take the one element here. I have lambda over n alpha to the k plus all the pi's that are not equal to the one element of non-crossing k of m pi times the Mobius function pi 1k. And notice that this number here, this is a number that's independent of n. Right, it has nothing to do with n. And here there are at least two parts, because this is not the one element of the lattice, and the number of summons is not dependent on n either. And this looks like at the best case 1 over n squared, right? Because when I have a partition here, each part is contributing 1 over n. So this will contribute 1 over n, but for any other element, there are at least two parts. So it's 1 over n squared. And now if I ask about the kappa k of p, which is I sum n such elements and which are free from each other, and I take the limit n goes to infinity, so I get lambda times alpha to the k. Okay, so I can write here plus O of 1 over n, but I take n to infinity. So this goes to n goes to infinity, goes to lambda times alpha to the k. Now from this, with machinery that we haven't seen yet in the lectures, we can get actually the distribution. Like I can write it as a formula like we did for the central limit theorem. However, I don't want to at this point. I want to just notice that this is a very clean formula for the cumulants of the. This is a very nice formula for the cumulants of the what I call the free Poisson element. It kind of resembles what we've seen for the square of the semicircle. Right? If I take the special case in which lambda equals 1 and alpha equals sigma squared, and sigma is just a parameter for the semicircle, I get that the square of a semicircle is a Poisson. Now, why is this interesting? What is the semicircle? Let's recall what we know about it. And we started by deriving it as a result of the central limit theorem. So let's have a little diagram here. If I start with Bernoulli random variable, sometimes I mean, Bernoulli is typically 0, 1, and Rademacher is for plus minus 1, but let's ignore the scaling and centering part. I can take the sum over n of them. So what do I get as a sum of n Bernoulli random variables? No, independent, sorry. Independent random variables.
Oh, binomial.
Binomial, right? And when we take n to infinity, up to scaling and centering, we get the normal, right? We get the Gaussian distribution. Right, this is in the classical independent case. What we've done in the free analog of this, we again take the sum, this isn't. Take again the sum of, let me already call them d such random variables. And we started by taking d to infinity, and we got here the semicircle. And at the point we did directly this move, next week Gil will show what's the missing piece here, which is the equivalent in this analogy of the binomial. This is going to be called the Keston-McKay distribution. But the semicircle is the analog of the normal. What you would expect if I say here that the semicircle squared is a Poisson, is a free Poisson, I would expect that the normal element squared be the standard Poisson, a special case for the standard Poisson. But this is definitely not the case. There's no, like, something happening in the free world that does not happen in the independent world at all. Normal element squared is not a Poisson element, which happens here, as we've seen. And this happens for a very, without going much into detail, this happens for a very interesting reason, which is the following, and I'll state it quickly. We've seen and sort of glanced over it as something obvious that if I look at the non-crossing partitions of n elements and the non-crossing pairings of two n elements, these turn out to be the same number, right? This is the Catalan number and this is the Catalan number. And we sort of glanced over it and didn't make much of it. But if we look instead of the world of partitions and pairings, nothing like this occurs here. So we know what this number is, right? You recall?
Just for eyes, Catalan.
This is the double factorial.
No.
Right? This you pair. You need to choose a pairing for the first element and then the third one, or etc. So this is equals 2n minus 1 times 2n minus 3 and so on.
Wait, no. So it's 2n minus 1 double factorial. Isn't?
No, it's the
That's the
notation.
Okay.
I think this is the one, but it doesn't really matter. This is definitely not what happens here. You know what these numbers are called?
The number of the second kind.
This is Bell numbers, but there is no closed formula for them. And it's
the sum of the Stirling number.
Oh, it's the sum of the Stirling number. Yeah, I didn't even remember that. But so something very clean and very pretty is happening in the non-crossing partition lattice, which does not happen at all in the overall partition world. And this tells us, although we started with, well, we're trying to do an analogy of like whatever we've seen in the in independent random variables, we're trying to produce the analog in the free world. However, surprising things happen that may have more structure than like we do expect now after we've seen this. See maybe more phenomena happening that we didn't know an analog of in independent random variable. So this is like even, I mean, for the semicircle we can draw it. I didn't write the explicit formula for this, even though it's not difficult to do this even without the free tools. But just the notion that the square of what's the analog of the normal element becomes the Poisson element is pretty surprising. That's it for today.